en el Centro de Investigación en Astronomía y Astrofísica Herzberg del National Research Council of Canada. Es jefe del Centro Canadiense de Datos Astronómicos. Es profesor adjunto en la Universidad de Victoria y en la Universidad de Columbia Británica y un experto mundial en el estudio del sistema solar exterior. Ha desempeñado un papel clave en programas internacionales de observación de cuerpos menores, incluyendo el Canada Friends Ecliptic Plane Survey y el Outer Solar System Origin Survey, además de ser co-investigador en la misión New Horizons de la NASA hacia Arrokoth y KEM-2. También es co-líder del Taiwanese American Occultation Survey 2, TAOS-2, un proyecto de colaboración entre la Academia Cínica de Astronomía y Astrofísica de Taiwán, la UNAM, el Centro de Astrofísica Harvard-Smithsonian y el National Research Center de Canadá, diseñado para detectar ocultaciones producidas por pequeños objetos del cinturón de Kuiper con alta cadencia temporal. El doctor Kavelaars fue el científico fundador de la plataforma Canadian Astronomy Data Centers, dedicada al procesamiento de datos astronómicos en la nube, y ha contribuido ampliamente al desarrollo de la infraestructura digital de investigación de Canadá, tanto a través del liderazgo nacional como de asociaciones internacionales. Su trabajo conecta la ciencia planetaria, los sistemas de datos astronómicos y el diseño de relevamientos observacionales. Y hoy pues, nos va a hablar de esta área, de su tema. So thank you very much for being here, and please go ahead.
Thank you. Gracias. Thank you. Thank you to the organizers for the invitation to come. And I hope that the presentation is interesting and somewhat comprehensible. So I introduced here as the someone who's very interested in how the processes of planets formation works. How do planets form? What is the process? But that is not where I started to do the work that I do. It was with this kind of object. So this is a comet, and it's active. You can see a beautiful tail of material coming off of the comet. This is another beautiful comet. You can see many of these in the sky all the time, more of them. And here's one where you can see in real time, this is an image taken with Hubble, one sequence after another, the comet breaking apart. So when I look around, I see a lot of very young astronomers here, a lot of young physicists who are eager to learn things. And I think a question you may ask your parents, your mother some time ago, where do babies come from? Yeah. Okay, it's the same for comets. Where do comets come from? How come there are comets? We see them breaking apart today, but the solar system is 4 billion years old. For 4 billion years, comets have been appearing and breaking apart and disappearing. What is their origin? Where do they come from? This was a question that puzzled many people for a long time. In the 1950s, two astronomers, two physicists, Edgeworth and Kuiper, proposed an idea of where the comets we see are coming from when the comets are orbiting around the sun in a plane. And the origin was somewhere beyond Neptune. And so today we call this region often the Kuiper Belt, sometimes the Edgeworth Kuiper Belt, sometimes the trans-Neptunian region. And when I was a young graduate student, finishing my undergraduate and starting school, there was no known object from this reservoir that might exist. We thought it should exist, but no one had ever found an object that was indicating that it existed. Even though we know that these things break apart. They're very beautiful. You can spend your whole life looking at these pictures. Oh yes, this is a picture of the observatory where I work. And is a comet Neowise, is the name of the comet. And it was taken by a friend who had to climb to a particular spot on a hill nearby to get the right angle to make it look like the comet was crashing into our observatory. Yes, it's a very beautiful photo. Okay, and here's another comet that I want you to remember the shape. Okay, the shape is like a tube. It's not a round thing. This is the core, the nucleus from a spacecraft that flew close up to this comet and can see that it is made of two pieces, a big piece and a small piece, kind of stuck together by a middle neck. Okay, so if you want to just know what do I plan to tell you, this is it. That planets, they grow from something called planetesimals, which are basically small planets. But the comets are today the planetesimals. Okay, what we see today as comets, they are old planetesimals. And those comets, they come from the Kuiper Belt and an area called the Oort cloud. Different kinds of orbits for the comets, different region where they come from. The planetesimals formed in the Kuiper Belt. That is where they were made. Okay? And we have seen interstellar comets. There's one coming through right now. It's very lucky. We can see images taken of it all the time. So it is a planetesimal from another star. So it tells us that the universality, that there must be planetesimals made around other stars. It's really amazing when this is a core part of physics, right? Everything is ordinary. Nothing is special. Our planets come from planetesimals that formed into comets. Other stars have also got planetesimals forming, making it probably into planets. And we see those planetesimals passing near our star. So we know for a fact that they exist. Okay, so these are planets. I think you're all very familiar with the planets. There's some big planets and there's some small planets. When I'm talking about the formation of planets, if you were in some of the seminars this morning in the astronomy section, you saw formation of giant planets through gas streaming through the disk and accumulating onto the planet. I'm interested in the core, the thing that started at the beginning, the very center piece, the core of the planet. How did it form? How did the core of the planet form that the gas eventually would stream onto to make a giant planet? Really very small planets. But the giant planets have a lesson for us, and that is that we will remember. If we look at Saturn, we see the rings of Saturn are very, very thin. They're incredibly thin, stable structures. And that tells us the nature of how disks behave, right? We learn about the disks from Saturn's rings. Okay, these are not planets. Here's a whole bunch of things in our solar system that are not planets, and these are the things that the planetesimals make. And if they get big enough, they become planets, okay? So we have Earth's moon, and we have Callisto, and we have Pluto and Charon, Titan, the giant moon that has an atmosphere, all these small things that build up to become the planets by having planetesimals accrete to form them, and then more things come later. And just more, just to get an idea of the sizes. So I'm going to talk about the Kuiper Belt. So there's the Earth and the Moon. And you can see the biggest Kuiper Belt object, Pluto and Eris, are basically the same size. And they are not as big as the Moon. Okay, so this is the picture of how planets form. This is a video that was made by the Herschel Observatory before the Herschel telescope launched, to kind of explain what they were trying to do. And it's kind of like magic, because somehow, look, the planets, something forms, these little planetesimals, and they get sucked up and they form into planets, and voila, we have the planetary system. So the research that I want to talk about is how do we know this process and how did it work? Because at the time of Herschel's launch, other than an artist's rendition of this, you don't really know how really the planets are forming. Okay. So understanding planet formation is a really difficult problem. It goes over many orders of magnitude, 13 orders of magnitude. You go from the tiny dust grains that are micron sized through objects that are centimeter to meter sized, all the way to things the size of Jupiter. And when people talk about planet formation, they're talking about the processes that span these 13 orders of magnitude. Okay? Ryugu, the Hayabusa 2 mission landed on it and brought us back dust particles. We had this interplanetary dust particle that was captured by a spacecraft. We have Arakoth, which is a small object that the NASA mission flew past, and then Jupiter, this giant object. And of course, there's many things in between these scales, but this just gives you the idea of the scales. Okay, so what happens? Where are the problems, right? So we have these barriers that stop planet formation from happening. When we have micron-sized dust, it kind of can jiggle about. The heat of the local disk is enough to make the dust kind of jiggle a little bit. And as it's jiggling around in its Brownian kind of motion, it gently runs into other dust and it can get a bit bigger. But as soon as it jiggles the area around it too much, it stirs the medium and the encounter velocities between the objects grow. And as they grow, they get so large that when two things hit, they're going too fast, they don't stick, they bounce. And when they bounce off each other, you can't get bigger. So we call this the bouncing barrier to planet formation, where the stirred up velocities are too high and things are bouncing off of each other. And this is a barrier to planetesimal formation that stops planets from forming. So we don't have a way of making planets if we can't get somehow past the bouncing barrier. Okay, let's say we figured out a problem and we found a solution to the bouncing barrier. What is happening next? So the particles get up a little bit bigger and they grow to tens of centimeters in size, and they start to feel the gas in the disk they're in as a wind blowing against them as they orbit. So they feel this frictional wind, they lose momentum, and they spiral in towards the star, and very rapidly they're removed. So we got over the bouncing barrier to make something a bit bigger and immediately have a different barrier, this kind of disk streaming problem where the dust will just collide into the central star and be gone. So these are the two problems that we try to solve by studying the Kuiper belt. How do we get over this bouncing barrier, and how do we get past this streaming problem? So it was known for a very long time that turbulence and gravitational instability could be the way to make the solution. People have known about this for beyond my lifetime, so more than 50 years, more than 60 years. But nobody is able to come up with a good mechanism for the instability to be set up in the disk that is like the solar system, okay? For many, many years, people tried to make this work. Under the correct conditions, you could get these clumps of planetesimals to form, getting all the way up to kilometer scales, but how do we get those conditions? And so Yudin and Goodman in 2004, they came up with this idea of something called the streaming instability. When you see smoke rising and becoming unstable in the atmosphere and it gets thicker, self-gravity pulls it together. This streaming instability forms. The same thing happens in disks. And so perhaps this is the instability that causes planetesimal growth. If it does, then it would remove the bouncing barrier because the density would go up and you would have the ability to push things together by gravity. And it would remove the streaming, the spiraling in problem because you would have these streams of material and they would block the headwind, and so you wouldn't spiral inward. So this one idea solves both of these problems. So the question that they ask is, are the first gravitationally bound objects, the planetesimals, are they formed by gradual collisional growth or by the gravitational collapse of overdensities in these streaming instabilities, or some combination of those things? And maybe we can figure out planetesimal formation if we can understand what's going on here. Okay, so I was talking about comets and the Kuiper Belt at the start. And so let's go back to thinking about the Kuiper Belt again. And 1992, so I think a lot of people in this room were not alive in 1992. Okay, so for you, this seems like ancient history. For older people, this is like brand new information. Okay, 30 years ago, the first objects in the Kuiper Belt were found. Dave Jewett and Jane Liu found the first objects. And you can, when the first gravitational wave was detected, maybe you can remember the excitement this was causing. The same thing in the Kuiper Belt. The very first Kuiper Belt object is found, and it's an amazing, exciting time. And so many people, myself included, switched from boring fields. I was studying the nature of dark matter. Okay, nothing is happening in this field. Look, they have found a Kuiper Belt object. So we will go study the Kuiper Belt. And actually, in my classmates, we were sitting in the office thinking, this is the most exciting field to be in. Why is not everybody switching to this field? So if you are sitting in your graduate office and some discovery happens and it seems like the most exciting thing to be happening, go and do that. It is the most exciting thing to be happening. That is an inspiration from me anyway. Okay. And I did finish my thesis on dark matter, but I didn't do any more. Okay. In 1999, there's a website, a service called the Minor Planet Center run out of Harvard University. And they track all the Kuiper Belt objects. That is one of their roles. And in 1999, these were all the objects we knew in the Kuiper Belt. And this is an image taken from their website on January 28th, 1999, when I was making a proposal to study the Kuiper Belt. And you can see some of the objects have circles that are filled in, and some of them are just circles that are open. Because the ones that were filled in, we know what their orbit is, and we know where they are. The ones that are not filled in, someone discovered it, and then we lost where it was. So the beginning, in the first 5 years, discoveries were happening, but there wasn't enough people working in the field to keep track of all of the objects, and they became lost. And the ability to do science was very limited. However, you could have great ideas. So these are two simulations that show basically the same thing. They show a disk of planetesimals and the giant planets and what would happen to the planetesimal disk. And you can see in both of these simulations, at some period, the disk causes the planets become unstable, and all the material in the Kuiper Belt area is scattered away. One of these models, the instability happens at 890 million years. The other one, it happens at about 10 million years. Both are models that were discussed. People are more inclined now to think, no, it's probably short, not so long. Both of these are instances of what we call the Nice model. And this model was conceived of when we knew only about those 10s or 20s of objects that were in the Kuiper Belt. This is a very brave extrapolation of what could be causing what we see, because the orbits of those objects are not like Saturn's rings. They are on crazy inclined orbits and highly eccentric and plunging in and out of the solar system. And there was no way they could have formed in that way. So what was a mechanism where they could form in one place and be transported to another? That was the goal of the Nice model. And so it managed to reproduce what people saw in the scattering of material in the outer solar system. You can see that in one of these models, there are more than 4 giant planets to start with. Today, when people are doing research, most of the time, we start with 5 giant planets. It produces a better outcome than only having 4. So it tells us that probably in our ancient past, in fact, the solar system didn't form 4 major planets, but rather 5. So this is really insightful information you can gather by studying the Kuiper Belt. Okay, what we hope to do is something like this. This is a plot that I will talk a little bit about. It is the asteroid H distribution, H or V0. These are the magnitudes that an object would have, how bright the object would be if you were standing on the surface of the sun and the object was at the Earth. Okay? So you're standing on the surface of the sun, the object is at the Earth, and you are just looking at this object. How bright is this object? And the bigger the object is, the brighter it will appear. And so this removes the distance effect, right? The more distant objects are fainter as well. So we take that out, we put everybody at the distance of the Earth, and then the angle of illumination matters, so we put the observer at the sun. And so the observer is on the sun, the light is shining from the sun to the object, hitting the object, coming back to the observer. How bright would it be? So that is this H magnitude or V0 magnitude. And it relates to the size by this equation you can see here. So the diameter of the object is something like 1,300 kilometers divided by this square root of p. This is how shiny the object is. And then you multiply by its brightness. And because the brightnesses are in logs, we take the 10 to the power of this thing. So the brighter objects are bigger and the smaller objects are smaller. What's really exciting about this is that we could see the distribution of sizes. As you go to smaller objects, because it's magnitudes, the smaller things are larger numbers. So around sizes of 14 are very small objects, around sizes of 4 are the very big objects. And as you go to smaller and smaller objects, the slope goes up as 0.5 on this plot. And this tells us the asteroids collided together and came to equilibrium in their sizes. So there were so many collisions between objects that eventually you just had the equilibrium distribution. So that is a really powerful thing to know when you have hit equilibrium. It also means that looking at the sizes of the objects tells you nothing about how they formed, because the distribution of sizes is not a formation outcome, it is a collisional evolutionary outcome. So you don't learn about the formation process of asteroids by studying their size distribution. You learn about their collisional history. Okay? And there's a little bump in there, and the little bump tells you a little bit about the formation process, where it goes from one slope and then it goes down and goes to another slope. In the Kuiper Belt, the first work, so remember Jewett and Liu, they discovered the first Kuiper Belt object. They did a lot of studies of the Kuiper Belt objects, and they tried to also measure how many objects are there as a function of size. But because very difficult to track and know where the objects were, we didn't do it as a function of how big they were, but just how bright they were. But they're all so far away that the brightness is not that important. The distance is not that important. So they measured it, and they saw that it was also a slope of about 0.5. And so people said, oh, it's the same as the asteroids. There's nothing to learn from the formation because the size distribution follows that equilibrium slope. And this was the very beginning of trying to understand the work. And you can see two points where there are arrows pointing down. And those are two surveys where they did years and years of work and detected no objects. So those are upper limits, and many of you will do research where you will plot upper limits because you will not be able to measure the thing that you hoped to measure. But you still are making important contributions. And in particular, you can see the upper limit, the K, pointing down at 500 kilometers. That was from Kozai, from Kuiper, who was trying to find the Kuiper Belt, okay? So there's something there about how the shape kind of drops down, but people didn't see the signal. What they saw was it was flat, and so it goes by 0.5. In the same time, I was working with a Professor Gladman at University of British Columbia. We were doing the same measurements, and we were getting a different answer. We were seeing that the slope was actually very steep. These plots look almost the same one to the other, except that you can see we added a point at 26, so very, very, very faint. And another point was added, super faint at HST, which later was retracted because it was a bad measurement. But the slope is quite steep. And so how can one person be seeing something that's so steep and the other group is seeing something that is so shallow? What is going on with this. We're looking at the same objects. What's going on? So we saw this, and we said this can't be from collisions. This must be from formation. And so we began a journey of trying to disentangle these two things. But we only had these small numbers of objects. However, today we have a much different picture. So I'm trying to show you here an image, and I don't know how good it shows on the screens. It has the original population, and it has all these very, very tiny dots that show all the objects we know of today. So now we know of about 3,000. So instead of trying to measure something from tens of objects, we can measure it from 3,000 objects. Okay. At the same time, we started to learn about the planetesimal population in the Kuiper Belt and what is going on. So here you're watching a movie of 6 objects that are not singletons, but rather they are 2 objects together. These are objects in the Kuiper Belt that orbit around each other. And they orbit around each other on timescales of a graduate career. They go very quickly around each other. And so we have some graduate students who were measuring. We detected, oh, look, there's 2 objects close together. And we went back a few months later and said, oh, they're still close, but slightly offset. And again and again and again. And you say, oh, they're orbiting around each other. They weren't just close together on the sky. They're actually in orbit around each other. And these binaries are just going around very slowly, one around the other. You can see they're kind of squiggly in their orbits because what we're plotting is how they look when observed. And so the Earth moving back and forth in its orbit causes a change in projection of where the object is. But this is very curious that they do this. I like this movie, so I'll try to play it again. See if I can do it. Yeah. So the strength of the binding between the 2 components is very low. Okay? When a baseball player hits a home run, they impart more energy to the baseball than is needed to disrupt these systems. Okay? They are a very strong baseball player. The Toronto Blue Jay. Okay, so they can hit the ball out. They would knock apart the binary. Okay, they're so weakly bound. Here's a picture of what would happen. Here's a binary going around, and the red dots are the binaries going around each other, and you see they orbit just in a few years. And then they get close to Neptune, and the orbit changes completely. And each time they would go past Neptune, they would have a big change to their orbits, and eventually they would become disrupted. So they cannot survive encounters with Neptune. You remember the picture of the Nice model with the planets going around, and all of a sudden, the whole solar system blows apart? These objects would not survive that time frame. They cannot participate in that kind of activity. And they require that they formed somewhere where they never got close to Neptune. And we call this area the cold Kuiper Belt, the low energy Kuiper Belt. Nothing is happening there, very, very quiet. Okay, so we started doing a survey in around 2005, looking for these kinds of objects and other Kuiper Belt objects using the Canada, France, Hawaii telescope. If you have a chance to ever use this telescope, take that chance. It's a very, very good telescope. It provides excellent data, and it has a fantastic wide field imaging camera that captures a large piece of the sky. Here's that telescope in the dome, spinning around to show itself off. And at the very top, the shiny thing is the camera holder. And inside that big piece of apparatus is the camera. The camera is the size of the Taos telescopes. It's a very big camera. Yeah. And here it is, the camera beside a penny. And that is the part of the sky that the camera can see. So we use this camera to do this survey. And we surveyed the sky. This is an image of the sky where the yellow is where the stars are. And the whole sky in one image on this projection. And then here are all the places on the sky we looked to find objects in the Kuiper Belt and other places. We looked for objects that were at the pole. We looked for objects that were in the plane. And because Hawaii is in the north, we only looked in the north. You can see a line of the galactic plane. You can see the ecliptic line from where the blue fields are. Yeah. So doing that, we found all of these objects in the outer solar system, and they tell us lots of things about the formation of the solar system. Here's a plot done in a scientist's kind of way. On the bottom axis is the distance the object is from the sun, or the size of its orbit. And the other axis is how tilted the orbit is. And I want to draw your attention to the things that have a distances of around 45 astronomical units and have very low inclinations, down below 10 degrees. They're in a disk like Saturn's rings, it's going around the sun. A very stable configuration, long-lived. This is this thing we call the cold belt. That is where those binaries are, where we know that nothing is disturbing this region. I can zoom in a bit on this region so we can see it more clearly. So now we have the semi-major axis and the inclination, and just looking in this very tiny box between 40 and 50 AU and 0 and 10 degrees. And I specify it's the free inclination. That is to say, we take out from the orbit perturbations that are caused by Neptune and see just how flat and thin the disk is. And it is below 4 degrees of inclination. If Saturn's rings were inclined as much as 4 degrees, they would look like a big schmozzle. Okay, so this is actually a lot of inclination, but this disk is so far from the sun, it doesn't really cause much of an issue. So we will look just at the low inclination objects, this cold objects, because they are there since the beginning of the solar system, because the binaries don't survive the encounters with Neptune. So we just everything below 4. And now we look at their distribution of sizes. The orange or yellow span is density distribution of how many objects there are as a function of size, where I'm giving the size now in these H magnitudes. So they're like you were standing on the surface. If the object was at the Earth and you were standing on the sun, this is how bright that object would be. But I have a couple of markers for you of where things of about 18 kilometers radius would be, or 16 kilometers, or 6 kilometers radius. And they're very large dots at the beginning at around 5. That's a few hundred kilometers in radius. And we can see that it is not a single line. It starts off low and it goes up gradually till it hits some asymptotic slope. If you think back to the very first plot I showed, where people were trying to measure the size distribution and they were getting a number of about 0.5, but they had it all kind of, there were all these points, these null observations that were below that line. They were already seeing it then, but the evidence was not strong enough. And now we see for sure that there's a tapered distribution. It goes along and then it collapses out. This cannot be collisional. This is not something that happens from collisionals. This has to be something from formation, of how planetesimals form. Okay, this streaming instability, a lot of work has been done on it over the decades. So this is a more recent simulation from 2024. And it shows in 2 projections a bunch of material streaming along, clumps forming, and the yellow dots you see are planetesimals forming in those clumps. I'm going to play it again. The green dots are easier to see. So you can see the streams, and clumps form in the streams, and things form. And so there's gas pressure in there, but the objects are not streaming inward because they're captured in these streams, so they're not being dragged inward towards the sun. They're not going so fast that they have bouncing. It forms planetesimals. So the streaming instability process works. It is the way that we can get over the gravitational instability, but do we have any evidence that it's really what happened? And so we look at the size distribution of the material that comes out of the streaming process. And what we see is that it's flat. Okay, and now I've plotted these, I made 2 plots. One is my plot, which goes in H, which is size on one axis and number on the other, but the size is given in these H units. And as we go this way, we get to, or that way, I guess, on your screens, we get to smaller and smaller objects. And for the simulators who do it, ABOD et al. Is a simulation of the size distribution you get from a streaming problem, and that goes exactly the same way. It starts off really sharp and goes off to some taper. I think I made a plot. Yeah, I took the data. The people who work on this said, "Why don't you plot in the same axis as us?" So I said, "Okay, I make a plot for you guys in the same axis as you do." So the bottom axis is now the mass of the object, and the top axis is the number of objects. And these two curves, they're not exactly the same. They're not reproductions of each other, but it is a model of planetesimal formation that naturally produces the observed distribution of sizes that we see amongst these low inclination cold objects that we think we know a lot about. You can see the parameters of this particular shape. There's P prime is between 166 and 183, and over on the other side, P is around 1.3. It's a similar range. On the one side, B is 1, the other side, B is 0.3. Not exactly the same. So there's work for the simulators to do, the modelers, to get the model to produce exactly the right numbers, because we measured the universe and we know what the numbers should be. And it's early in this field, and so you have a chance to come in and help figure out how to make the streaming instability produce the right answers. All these different colors are different initial metallicities of a disk, basically how much mass is in the disk. Okay, so then we went off and we flew a spacecraft into the outer solar system. This is the New Horizons spacecraft. Has lots of instruments on board. The one I want to draw attention to is the one called LORRI. It's a tiny telescope, about, try to remember, it's 12 inches or 12 centimeters, I don't remember which, across. It's a very small aperture opening. I think it's 12 inches, but I'm not 100% sure today. And we flew this through the Kuiper Belt, trying to measure Kuiper Belt objects. So that is what the Kuiper Belt looked like in our models of what the Kuiper Belt should look like. Each of those dots is a Kuiper Belt object. The orange dots are objects in this low inclination disk that is out there in our model. And the yellow line is the trajectory that the spacecraft will take. And so we searched along the yellow line for something for the spacecraft to observe when it got there. And we found an object. So here it is going along. There's the little triangle, which is the spacecraft, and it goes whoosh past Pluto, and then whoosh past to some other objects that we saw. You can see that they're all in a group because we were looking along that line of sight to try to find them. And I'll just do that video again. So it's flying along. The red dots are the low inclination cold objects. The lines show the orbits of all the objects to get you an idea of the structure of the system. And then we just fade out all the other objects and just show that cold disk of material. So the spacecraft flew past this object Airkoth that's in that low inclination part. And I just want to remind you that, remember, we had this Donier thing, and the slope goes to 0.5 when it hits equilibrium. And if I can be so bold, go back a bit to this plot. We couldn't tell if here the slope also goes at the tapering end to 0.5. Maybe it goes to 0.5. Maybe at the taper end, where it starts to get flat, it goes to the same slope as the slope that we see for equilibrium. Okay, so we flew the spacecraft along, and before we got there, we made a prediction. Oh yeah, and the object now is known as Airkoth. But in the planetary science community, we start off by giving them strange acronyms, and this object was called MU69, 2004 MU69. Okay, we made a prediction. If it was 0.5 and it just went 0.5 at equilibrium all the way up, and we counted the craters, we would see a flat line for the number of craters per unit size. So on this diagram, crater size is the axis this way, and number of objects is this way, but it's not given in total number of objects, it's given in how many objects would you expect if the slope was 0.5. If it's a flat line, the slope was 0.5. If the line goes up, it was steeper than 0.5, and if the line goes down, it's shallower than 0.5, okay? And so we made a prediction that we would see these blue lines. Oh, okay, thanks. So we flew past the object. Oh, there we are. That's Arikoth, the very first image downloaded from the spacecraft. It was a very exciting moment. We saw a little snowman on our screens. It's just an incredible point of discovery. There it is, what it looks like when you zoom in a bit. And if I go here, you can see these are the best 2 images we took. The spacecraft mission took 9 years. We have 6 very good images. Okay? This is what you get in science. Okay, and you can see these little craters on the edge where the sun's illumination is at an angle. You can pick out the craters. Okay? The craters are caused by things hitting the surface, very small things. This object is only tens of kilometers across. So tiny little things, 1 kilometer objects, are hitting it and causing craters. And we want to know how many craters are there for every size. So there's a round in the middle. You can see this kind of circle that's 7 kilometers across. But you have all these craters in the shadowy area that we could count. They're very tiny craters. And so we counted them and they look like that. So the slope is much, much shallower than 0.5. It's like 0.2, okay? 0.15, super shallow for craters of diameter 1 to 10 kilometers. Impactors, a 1 kilometer impactor makes a 10 kilometer crater. So these are something like 100-meter objects to 1 kilometer objects. You can never see these from the ground with a reflective telescope. They are 32 magnitudes in faintness. They're impossible to see. But we can see that the number drops dramatically with size as you go to smaller sizes, which tells us nothing in equilibrium in the Kuiper Belt. We really are measuring the outcome of planetesimal formation when we do this. So how can we measure more of these small objects? There's a facility that's being built. It's almost operational. Is operational. It's very close to operational, TAUS 2. It's being used to do test observations right now. These 3 telescopes will point at a star, and when a tiny, tiny Kuiper Belt object of only a few kilometers or 1 kilometer or even less than 1 kilometer passes the star, it will occult it. The occultation will be only for a few tenths of a second, so there are 3 telescopes to all see the same event, to know for sure the event happened. And using that, here in Mexico, we will measure how many of these small objects there are. We have one estimate coming from these craters on this thing, but we only counted, you can see each crater is numbered. We counted 43 craters. So the entire understanding of the process of how planetesimal formation is occurring at these small scales is based on just these 43 measurements. But with TAUS, we will add many, many more measurements to that data set to get a better understanding. This is what an occultation looks like when you see it from such a small object. And I point this out because it's a physics audience, and so it's very exciting to understand physics at this scale. So if you're in the lab, in undergraduate lab, you're doing diffraction experiment, where you're shining a laser through a tiny slit, and you can see the interference of the light waves on a screen, causing a pattern on the screen, right? You see this Fresnel pattern, or Fraunhofer diffraction, depending on the scales. You see the exact same phenomena, only now the laser is replaced by a star that is hundreds of parsecs away. The slit is an object of a kilometer in size in the outer solar system, and the screen is the Earth. But that scale reproduces this diffraction effect, which tells you that the nature of the wavelength of light, right, is behaving exactly like you expect it to, but not on nanometer scales, but now the whole apparatus is astronomical unit scales. It's astronomical in size, but the same physics is happening. And using that physics that you can measure here in the lab, you can determine the sizes of the objects using TAUS 2. This is what a time series will look like when we measure a star. The star will get brighter, the star will get dimmer, the star will get brighter. The Earth is moving through the screen and seeing the bright, dark, bright, dark, bright, dark bands of the diffraction. So that will be finally measuring the outcomes of that planetesimal formation process. And there it is, the 3 sites at the San Pedro Martir on the Baja, ready to go. So hopefully we will make these measurements and have an outcome of really nailing down the processes that lead to planetesimal formation, to constrain properly how the streaming instability process works. But we think we're very close to bringing together the whole problem of how planets form. So, one last set of things to think about. The Atacama Large Millimeter Array is a radio telescope on the Atacama. And you were looking at these disks today in one of the sessions, right? There's these disks of dust. These are the dust out that results after the planetesimals form, and they produce, when they collide together, they produce these rings of dust, or they can be rings of gas and dust together that are witnessing the processes of planetesimal formation. We see a lot of structures in here that remind us of the things we think will come when we understand the streaming instability completely. Here's even more of them. They're just a fantastic menagerie of these kinds of structures. So we can extend the ideas we have here to other stars to understand planet formation around other stars. And here we have, so this was a slide I made before the most recent interstellar comet. They're just going to keep coming, right? More and more interstellar comets. It's going to be very exciting. And this is a messenger from another star to tell us that the same process is happening there. This is a plot that I just want to draw your attention to. It's what time and how many objects are discovered. And you can see that in 2024, we stopped discovering objects because everybody is holding their breath for this new facility that begins operation maybe tomorrow. It's very, very close to being fully operational. It's a fully operational Death Star, ready to kill the problem of what is the structure of the Kuiper Belt. And here it is in the dome of that building. And that is the camera that will gather the light, and it will detect, instead of having 2,000 or 3,000 Kuiper Belt objects, we will have 30 to 50,000 Kuiper Belt objects that we can use to fully understand all of the processes that went into the planets being constructed and gather up the planetesimal formation. Thank you for paying attention.
Thank you very much, John. It's been a super exciting talk. And now, okay, podemos iniciar el turno de preguntas. Seguro que hay muchísimas en la sala. Hay varios micrófonos repartidos por toda la sala y por aquí hay algunas preguntas. So, yeah, we start the questions.
Thank you for the talk. I want to ask, what about the Oort cloud structure?
Yes, so using a facility like TAUS, we can also see objects in the Oort cloud. And so we could detect them. They will be much bigger objects farther away, but there's a chance that TAUS will also find Oort cloud objects. What will work better is to build a space observatory that measures occultations, because the signal will be very, very weak from the Oort cloud. So we have a number of proposals already have been made to build an Oort cloud explorer in space. But first, TAUS has to show us detections from the ground, and then we can do it in space. Yeah.
Thank you.
Good afternoon. Well, the doubt I had is, how do we consider the age of a star that is well, the formation of the the planetesimal? How do you consider that fact, that information, that heat in the formation?
Yes, yeah. Where does the star's age play into the process? So when we look at the disks where we see planetesimal forming, it happens in the first 100,000 to 1,000,000 years. It's very quick from astronomers' perspective. And in fact, the whole process probably only takes a few orbits around the star. And when you make the disk to do the streaming instability process, you have to put in the pressure from the solar wind, the heating from the photon heating, ionization that is happening, all of those parameters will be folded into this modeling to know which one is controlling the distribution of the sizes of the objects. So there's a critical thing to know is what kind of star is allowing planetesimals to form. Yeah, yeah. Thanks.
Good morning. I just wanted to ask what kind of information we can have by understanding how the core was formed.
How the core was formed?
Yeah, what kind of information we could have with that?
Yes. So it's really about the efficiency of the processes of planet formation that we're trying to get a handle on. In the previous models from the 70s and 80s, you had to have a very, very massive disk to form a core in order for the gas to accrete onto the core to create a giant planet. It may be that you don't need to have so massive a core, and that even you don't need as much dust material to form that core. And you can trigger core formation very early and very rapidly go from no giant planet to a giant planet. And so this tells us about what the process is by which you can get to a giant planet formation, and ties into our trying to understand basically the whole range of processes that go on. So, yeah.
Thank you.
First, okay. Well, two questions, quick one. The first one is related to Planet 9. I know you don't like that. Well, take yours. You can see it if you want. What do you think about the existence of this planet based on what you know about the Kuiper belt now? And the second one is once Vera Rubin extracts a bunch of a lot of objects there, what you guys are working in the Kuiper belt will do?
Uh-huh. So I'm going back to a slide that I showed, and I thought I had it handier, but I have to go back. Just a little more back. Come on. There.
Yeah, because you said in your simulation that they are using in the NIS model. You are using five.
Yes.
Five planets
right.
instead of 4. Yeah.
Yeah. So the Planet 9 idea is that there are objects in the outer. There we go. There are objects in the outer solar system that have these really extended orbits. So this one that is labeled RR245 has a super long orbit that is difficult to create with the known solar system. How do you have something that is never getting very close to Neptune, which is the outer blue circle, but is scattered to this large orbit? The other object is Sedna. Sedna also has an orbit like this, which is extended and scattered outward. And we don't understand how they get onto those orbits yet. When we look at, there are 3 objects where really they never interact with Neptune. We know of 3 objects in the outer solar system that never really interact with Neptune. And they're on these large extended orbits. And the pericenter, the location on the orbit where the objects are closest to the sun, are all kind of close together. Maybe this is caused by an effect from another gravitational body, Planet 9. Or maybe it's just because when things are close, they're easy to see, and those were all discovered at the same time of the year, and so that's why they're all in that part of the sky. There's a lot of debate about which is the answer. I have a joke I make, which is there's no evidence that there is a 9th planet. But when they find the 9th planet, it will be very exciting to work in this field. Okay.
Yeah. Thanks.
Okay.
But the second question was what will we do once?
So unfortunately, Rubin LSST will never find more objects to help with this problem. Its flux limit is too bright to find these really distant objects that are having this problem of their closest approach being too far away. So Vera Rubin is probably not going to get us to the answer about the planet 9. For that, we need to do other surveys with other facilities that will go deeper. The Canada-France Hawaii telescope is one possibility, but the Subaru telescope is one that has a bigger camera and will probably make a lot of progress on this question.
First, I would like to thank you for your presentation. It has been wonderful. Could you repeat what are the techniques used to face the occultation effect caused by small objects when you are studying the objects of the Kuiper belt?
What are the effects?
The occultation effects.
Yes. So, yeah. So let me go to the occultation slide. There we go. So I think this captures it here. So this is this image is if you had a circular aperture and a laser shining on the circular aperture, and then a screen in the distance, you would get this diffraction pattern on that screen. Only now it's not in a lab. The circular aperture is 1 kilometer sized object, or actually in this one it's 5 kilometers in size. This, huh? It's an obstruction, not an aperture. Thank you. Yes, and the illuminating source is a star. But the light from the star has traveled so far from where you are that the waves coming towards the object are like a plane. They're all aligned in a plane. They're not a laser, but the plane of the waves is uniform. And so they strike the object and they diffract or refract around it and create this kind of shadowing effect on the other side. But the shadow isn't like right beside the object. To see the shadow, you have to be millions of kilometers away. And the shadow appears, if you put a screen there, the shadow would appear. And in our problem, the screen we use is the Earth. And then, well, how do we measure? We could be in space and we could look down at the shadow that's on the Earth. But what's easier is to have a telescope on the ground. The shadow is static and the Earth is rotating underneath it. And so you pass through first you pass through a bright spot, and then a dark spot, and then a bright spot in the shadow. And so this plot here is showing a series of images in time, where you're looking at a star, and the red and black lines are the star being measured. And as the Earth moves through the shadow, the star gets brighter, and then the star gets dimmer, and then brighter. And in the middle, actually, it's very bright. Even though you're looking directly at the occulting aperture, and the star is directly behind it, the light has diffracted around the object, and is coming into your telescope, and you see Poisson's spot, the brightness of something which is directly behind an occulting mask. So something you can do in the lab. Yeah.
Hello, and thank you very much for your talk. My question was more about that you mentioned at the beginning that the planetesimals, we have seen some that come from interstellar regions.
Yes.
So you mentioned that your model, there's some instability that disperses all the planetesimals. Could that explain how those objects just get launched out to interstellar and miss both the Oort cloud and the Kuiper system? Because I imagine there should be a very strong slingshot effect to cause them to just go fly past the entire solar system.
Yeah. So those gravitational scattering encounters are very strong. The majority of them end up putting the object into the sun. About 1% or so end up putting the object in the Oort cloud. And then another tiny, very tail end of the velocity distribution can eject them from the solar system. And even if they're in the Oort cloud, a passing star that comes near to us can be enough to pull the object out and make it float freely through space. So the instability process we see generates interstellar comets. And so this can tell you that, oh, this instability process is also common. It's amazing, right? We see it in our solar system. People talk, oh, how special is the Earth and the planets and everything. But we see interstellar comets, which tells us, no, instability-driven planet evolution is how it happens. So, yeah.
Okay, thank you very much for your answer.
Thank you.
You told us that you had like a different result when of the slope when you watch the snowman. I just want to know if like that changed the model a lot because well, 0.2 and 0.5 it's quite a change.
Yes. Yeah. And so when they do the streaming instability models, right? I can go back one more. Oh, one more. Anyway, the slope was about 0.5 in the models they do today. And I asked the people who do this modeling, well, that's very different from 0.1 or 0.2. Okay, how come? And they say, because we don't actually know this slope very well. This is right at the resolution at the end of the simulation where the smallest objects are formed. And the computer time it takes to simulate such very fine-grained processes is not currently accessible for these projects. So they don't know really how shallow it goes. Does it go to 0.3 or 0.1 or 0.2? So, but they're very excited that we are measuring on Arrokoth 0.2 or 0.15, and so they want to also try to get to that value through their simulations. Oh.
Okay, so we might make one very quick last question, the last one. Okay.
Thank you. Why is it a belt? I understood that there is an inner limit, that's Neptune. Why there is, it looks as if there is also an outer limit for their position.
Yeah, I have a slide. This is not the way to go through slides, but okay. Come on, one more. So when we look at the Kuiper Belt, these are the orbits of objects that were discovered in a project that we run looking for things for the spacecraft to observe. And we see many, many objects at the inner edge where Neptune is. And then it peaks, and then it starts to go down. And there's a big gap where there doesn't seem to be very many things we find. And then we find more things as we go farther out. Why is this the structure of the Kuiper Belt? We don't know. What would cause the belt to end where it does? This will be a really important clue for the streaming instability or planetesimal formation models. It's probably links back to the question about the star. And as you get farther and farther from the star, the radiation environment is changing, the heating is changing. There must be some interplay between these things that is causing the truncation of the disk to form. We don't know the answer, but it's something that we hope actually we will use Vera Rubin Observatory to get more information about. Yeah. Okay. Thank you.
Okay, so let's thank John again. So I think we would be here asking questions for a long time more. I also had more questions to do. We are very grateful to John. He has made us a very great presentation, giving light on how the planet formation process might have been in the solar system. We are super grateful, and for this, we are giving him a present. It's a craft, local craft from Estado de Mexico, from Metepec. So it's a present for you. We are so grateful. So thank you very much. It's called the Tree of Life, made here in Metepec. So thank you very much.
Thank you so much for coming today. Yeah. Thank you.
On the contrary. Yeah, so this is from here?
Yeah, that's UL's, so.
Okay.
Yeah, don't steal it. Okay. Or this.